It's a class where I'm pretty sure if it was a book, it would be a lot easier.
All right. Let's go. Let's do this. Welcome to Lecture 15, Microcontroller Sensing and Control for CSC 5323, 7323. I'm sure we're all doing a lot better today. Good. Excellent. Good to hear. The class seems a lot bigger today, which is great. It's nice to have everybody back. Okay. So, let's go ahead and get started. So, course logistics A4 has a due date of this Friday. How many people are going to be done by Friday? One team is like, we got this.
We did spend a lot of time over spring break, though. Yeah. We don't have fun. I didn't have vacations or those.
Okay. So, what do you guys think about extending the deadline to Monday?
That's an amazing recommendation. It's the best idea.
Necessity.
Let's take a vote. I'm just kidding. I don't need a vote. Okay, so let's do this. We will make it due Monday. I want to make it due before class on Monday so that you're not working on it during class. There's no incentive to work on it during class. So let's say that it is due Monday, and I will hold special office hours before class on Monday, essentially like 1 to 3 before class. Okay? And you can show me then, if you want to show me Friday in my office hours, that's awesome. Do it. And that way Monday's freed up for you, and you can go and hang out this weekend while everybody else is working on it. Or not. I don't know. I don't know what you guys do. No idea. Okay. So A5 is due 2 weeks from Friday. A5 is due 2 weeks from Friday. Okay? Fair enough? The reason I consider this one special is because it happened over spring break. A lot of people that were like out of town and doing team logistics. So essentially, even though it was like a 3-week assignment, it wasn't really a 3-week assignment, and I know that. So we'll do that. I think that sounds like a good plan. That's fine. I don't see any problem with that. Right? We're not going to fall behind in class because we don't have tests. Okay. So the agenda for today, I want to continue discussion on using microcontrollers. That's with pulse width modulation. We're going to talk about GPIO. We'll talk about interrupts really quickly. Then we're going to go into something I like to call hobbyist electronics. This is not electrical engineering. It is hobbyist electronics, right? We're not doing electrical engineering in this class. Really not. But we are going to be doing some stuff that deals with sensors. But these are sensors that you would buy on SparkFun, right? You guys know what SparkFun is? Some people do, right? You can just buy sensors online, and they're in it's got a box from SparkFun right there. Okay, it's just you can go online, and it's like, I was like, here, buy this product, and here's a huge tutorial for using it, and maybe a couple videos. Right? And it's like, oh, and here's the spec sheet for it, and here's what we found from the spec sheet that doesn't actually work. Right? It's just a bunch of people that are hobbyists that got together and decided they were going to use a bunch of sensors. And it's great. It's awesome for rapid prototyping. It's what you should do before you make any type of final product, is go in and use this kind of thing. Okay? So we'll talk a little bit about potentiometers, magnetic switches. We're going to spend a little bit of time. I wasn't going to talk about this, but some people in class have actually asked if I could talk about servo control and motor control. And we'll spend a couple of slides on it. I'll do a little demo. For how to do that kind of control. So, like, I don't know, if one of your final projects was you wanted to create a quadcopter or something, control it from the iPhone, you would have enough kind of inkling on how to do motor control that you might be able to do that. Okay? So let's do it. And then we will get into the beginnings of Bluetooth. Maybe. Hopefully we'll get to the beginnings of Bluetooth in the lecture. We may not, and that's okay. Right? I'm running on about 2 hours of sleep, so I have no idea how fast or slow I'm going to go. Okay? Let's do this. All right, pulse width modulation review. What is pulse width modulation? What are you raising your hand? Are you raising your hand in my class? Just spit it out. No, go ahead. No.
It's when you flash, like, you only use binary ones and zeros, but you flash those.
You flash it at a certain frequency and at a certain duty cycle. Yeah, you create an artificial analog thing. That's perfect. That's good, right? That's perfect, right? So if you were lighting up an LED, this was the brightness thing, right? All we're doing is generating pulses, and each of those pulses, they're either really, really skinny, which means we're dimly lighting the LED, or they're really, really long, which means we're brightly lighting an LED, okay? So we're good. That's pulse width modulation. The way that it works in the hardware, it's a specialized hardware, right? So you're not sitting there inside of the microcontroller and saying, okay, make a pulse, make it high, okay? Wait for 100 microseconds, then set it low, and then wait for another like 800 microseconds, and then set it high. You're not doing that inside the microcontroller, right? The only thing that you're doing is you're setting a register value, and there's a special hardware that's reading from that register value, right? And you can be doing other stuff in the microcontroller. You set the register value and say enable pulse width modulation, and then you do whatever you need to do, and it will generate pulse widths on its own. So the way that you do that is you set that register value, you set up a counter that is going to compare its value as it's counting up to that register value. It compares the two, right? And then if it's ever above that register value that you set, then it sets a pin to low, right? And then whenever the counter gets back down to 0, it sets that pin to high, right? And then it gets the value you set, sets it low, right? It clears the bit, sets it low, right? So that counter, the frequency of pulse widths that you're generating with that, it's really important, the clock that you're feeding into your counter, because that determines how fast it's actually counting up and when it's going to surpass that value, right? So essentially, you have a clock with a divider that's coming down, right? So this is all review from last time, okay? And so if you're controlling the frequency of your pulse widths, you do it by controlling how much you're dividing the clock down that goes into your counter, right? And then also what the register value is that you're counting up to. That controls the duty cycle. Yeah? Good? Happiness? Everybody's happy. Okay, so we did that pulse width modulation with Arduino code. It was like 3 lines of code. It was awesome. Everyone was like, yes, this is perfect, right? The only problem with it is it's very, very limited control. And if you want a little bit more control with the pulse width modulation, then you can pay attention, right? If you don't want more control with pulse width modulation, just veg out until we get to ADCs, okay? Shouldn't have said that. All right, so pulse width modulation with registers. We went over this very, very quickly. This is code that allows you, this little underscore BV is setting a bit inside of a register, right? So it is setting the bit named WGM20 inside of the register TCCR2A. Man, whatever. Okay, so here is TCCR2A. It's essentially a timer and control register, right? It's controlling that timer for our pulse width modulation. So let's go into what this does. Inside of that register, inside of TCR2A, there are 2 bits, COM2A1 and COM2A0, right? This line of code sets COM2A1 to be logic 1. It sets COM2A0 to be 0, right? So we've now selected this 1, 0 thing, which means that we're going to have a counter, and the counter's name is tcount2. Okay? And what I'm plotting here is the value of the counter. It's going to count from 0 to some max value. It's actually 255. It's going to count from 0 to 255, and then it's going to go drop back down and count from 0 to 255. And it's going to do that for infinity, and it's going to feel really good about itself. Okay? There's a threshold value that needs to meet that we talked about before. That threshold value is the register OCR2A. That's the threshold value that you're setting that you want it to compare to. So I'm setting it equal to 200. So now, the control operation for bit OC2A is this, okay? So bit OC2A is on a compare match. When I'm up counting, I'm going to set OC2A when down counting, okay? This thing never, when is this thing up counting? When is tcount2 up counting? All the time. When is it down counting? When it just drops back down to 0. Okay, you could also set tcount2 to count up to 255 and then decrement down to 255. That's not what we're setting right here with our control register. We've set it to just do this. So that's pretty simple, actually. So whenever we're comparing tcount2 to one another, whenever it surpasses OCR2A, it's going to set this bit low, and then whenever it starts down counting on tcount2, it's going to set it high, and that's a pulse width, and we're all happy with ourselves, right? Same thing for OC2B. So I'm actually, with this line of code, we're setting up 2 pulse width modulation bits, okay, on 2 different pins.
Does the counter just count at like the full clock frequency?
Does the counter count at the full clock frequency? Do you know my next slide?
No.
All right. No. And that is set up by this 2 bits right here, which is WGM21 and WGM20, right? Actually, that may not be true. No, that's not true. Okay, so, but my next slide, we'll get to that. Okay? Okay. See, I don't even know this code. This is the beauty of working with Arduino is you don't have to sit here and look at register values to see what code does, right? Okay, this is obfuscated to me. All right? What? What, that you don't actually require people to really like dig down into your code to figure out what's doing? It would be cool. I mean, you could also comment this really, really well also, right? Okay? But essentially, what this does is it sets WGM21 and sets WGM20. So where inside of this, if these are the values of each of those, what have I selected? Node 3. Bam, right there, which is fast PWM. Right? Essentially, what that did is that told tcount2 to count from 0 to 255 and then go back down to 0. Okay? That's what those 2 bits do. Okay? And the only way you would know that is by meticulously reading the datasheet. If you're working with a microcontroller, that's what you're doing. This, my friend, this is where we are dividing down the clock. Okay? With this. There's actually a separate register called TCCR2B, and we're going to set the CS22 bit in it. What does that do, based on this table that I'm showing here? If we set CS22 and leave the others as 0, what are we selecting? 1/64th of the clock cycle, right? So I'm going to take my clock, which is 16 megahertz, divide by 16. What frequency am I running at now? I'll give you a hint. It's on the slide. I'm running at about 1,000 hertz, right? 976 hertz. The way that I got that was I took my 16 megahertz, I divided by 64, which was the prescaler I just set up, and then I divided that by 256. Why did I divide it by 256?
How many ticks of the counter you're going?
That's how many ticks of the counter. Counter goes from 0 to 255. There are 256 clicks, right? So every single time that's what the counter is doing, right? So it's running at 1K. Excellent. Awesome. We're feeling great. And then these, as we talked about these 2 bits before, these are the output compare registers. So I've set OCR2A to 200 and OCR2B to 120. All right, so what that means is that OCR2A is the little purple dot up there. It's higher than the green dot, which is OCR2B. So the duty cycle of OC2A, which is the bit, the duty cycle of that is 200 divided by 256, and that's 78% duty cycle. Okay? I did not divide that by 255. I divided it by 256. Right? Even though the counter is going from 0 to 255, and the value of that register is 200. Right? You would think that it would actually be, well, whenever it gets to 200, right? So 200 over 255. That's not the case. Okay? Good. The only reason I knew that is from the documentation. Okay, moving on. Good. Okay, so that's what it looks like. The duty cycle of OC2B, which is actually pin 11 on the Arduino. Where did I find that out? Yeah. I'll keep coming back to that. I'm going to nail that. You're going to Pavlov that. I'm going to say, from now on, I'm going to say, where did I find that? And somebody's just going to go, data sheet. Okay? Just Pavlov it. You guys know what that means? When I say Pavlov it, Pavlov dogs, drooling, look it up. You love it. Okay? Moving on. Okay, so, and then we already talked about the period of this assignment, or the period of the square wave. Okay, so we're good. We already went over those. Okay. All right, now everybody who wasn't interested in pulse width modulation, come back. Come on back. We're going to talk about the analog to digital converter. Okay? Let's talk about the ADC on the atmega. Right? So, and we'll do a pulse width modulation demo here in just a bit, but I want to do it with a servo. Okay, so the ADC converts analog to digital. When you're working on a microcontroller, it's a lot more explicit than when we were doing it on the iPhone. Okay? Because we're working at a lot lower clock frequencies, we have direct access to all of the hardware, honestly, that's on the microcontroller. There's a lot of things that we need to know about with the analog to digital conversion, and a lot of things that we have control over now that essentially iOS was kind of hiding from us. So the first thing is analog to digital conversion is going to be dependent on some reference voltage that we give the analog to digital converter. Okay? We'll give it a reference voltage so that it knows what these different voltages that come in are. Okay? It's also going to be dependent on the sampling rate that it can run at and the dynamic range of values that it can come back with. Okay? So on the Arduino, we have a 10-bit ADC, right? So you have 1,024 bits that you can work with. Question? Ah, it gives you 2 bytes. Only the top 10 of those mean something. The other ones are just noise. Yeah. Okay, so the Arduino has 6 analog to digital pins on it that have this dedicated ADC hardware inside of them. That's not actually true. It has 6 pins that are muxed together that connect to one ADC. Okay, it's got one little analog to digital converter hardware inside of that microcontroller. And the reason they do that is because that costs way less money. Okay? ADCs, they're big, and they're not cheap to put onto these chips, but they're needed, right? So if you can get away with, oh, yeah, we've got 6 channels, yeah, they all connect to the same ADC, but you can read 6 different pins. Okay? And as long as that ADC can run fast enough, I'll do a bunch of analog conversions in rapid succession, and you can get the analog values of all of those 6 different voltages. Theoretically, from the datasheet, this will run at 80 kilohertz sampling. Okay? That's pretty fast. That's faster than the iPhone does for audio, right? With audio, we were sampling at 44.1 kilohertz. Okay? The caveat here is you have to run at 15 kilohertz if you want the full resolution. So if you start running above 15 kilohertz, you start losing bits that are meaningful on the ADC, right? So you go from 10-bit to maybe 8-bit. Maybe 2 bits. All right, if you run it really, really fast. Okay? What does that mean? Less granularity, right? I'm trying to figure out what the temperature of the room is, right? And the way that I figure out temperature is by reading some analog voltage off of a temperature sensor, right? If I don't have the digital accuracy, I can't pinpoint the temperature within so many degrees. Real world example. Look at me go. Okay, so here's the atmega ADC. This is what it looks like on the inside. These are those 6 different pins. They connect to an input mux. And then this is where all of that analog to digital conversion occurs. Okay? Right? So there's a bunch of conversion logic. It is what it is. There's also connected up to this input mux. There's a dedicated temperature sensor that's inside of the microcontroller. So you have to read from this very, very slowly if you ever wanted to read from it. But there's a dedicated temperature sensor that you can select to run an ADC value and see what the temperature of the chip is. Right? It's kind of cool. It's built in.
It's also for skew because if you get huge temperature swings, ADCs drift.
A lot. Yeah. A lot. Okay, so you'll notice in here that there's, on the very top of here, there's a bunch of different things for selecting what your analog reference is going to be, right? It can either come from off the chip, or it can come from the internal reference that you have on the chip, right? So the way that you set that up is you can say in your Arduino code inside of your setup function, you can call analog reference default. When you do that, you're setting up a 5-volt reference, okay? What does that mean? They'll be compared to 5 volts. The max voltage that you can measure is going to be 5 volts. Anything above 5 volts is going to be 1024, which you'll get back on the pin, okay? If you get a voltage that comes back and it's 2.5, then what would be the value on the pin? The digital value that you would come back. If your reference is 5 volts, boom, 512, or maybe 511. Who knows? It's going to be fluctuating in there, okay? Right? You can also set it up to where you have a 1.1 voltage reference. This is good for sensors that essentially you want a really, you want better granularity, right? So you have 1,000 values essentially between 0 and 1.1 volts, right? 1.1 over 1024 values that you can come back with, okay? And you can also set up your own external reference that you can put on there, right? So you have some voltage reference, you buy it, you hook it up to the AREF pin on your microcontroller, and you call it good, okay? So there's a lot more control here then. When you want to read from it, here's how you do it. Analog read. A0. What does that do? Somebody tell me what that does. It reads the analog 0 pin. It's A0. And it returns 2 bytes, only the top 10 of which actually are meaningful. Okay? Very cool. Very cool. That's easy to do. Okay. So if I want to convert that to voltage, we do exactly what we did before here. I will read this. Okay, so the pin was A0, right? So I set up this value sensor, which is some analog pin that I want. I say, here's the data that I get back from it. When I want to convert that into a voltage, I cast data as a float. I divide it by 1024, right, which is my max volt, the max that I can get back from that ADC. And then I multiply it by whatever Vref is. And I've got the voltage now that's on there. Okay? Happiness? We're good on analog reads? What's the problem with this? Does anybody know has anybody ever used the analog read function on Arduino before? Did you ever have to sample fast? Did you? If you did have to sample fast, you would know that this method is really slow. It is not taking into account the full power of your microcontroller. Okay? So how are we going to make it faster? We're going to do it ourselves. How are we going to do it ourselves? We're going to look at the data sheet. Yeah, that's going to be like the de facto answer from now on. Data sheet. We're going to look at the data sheet. Actually, we're going to use the data sheet and we're going to use some Arduino code, right? Because this is a little bit easier. So here's what we can do. A fairly fast conversion is we can set up our own prescaler, right? And this is the prescaler that controls essentially the clock divider that goes into our ADC, right? So this is how long we're going to wait before the microcontroller says, hey, I have a good ADC value, right? So there's these 3 bits, ADPS2, ADPS1, and ADPS0 that set up the prescaler, right? The bigger the prescaler, the slower the clock, right? So when I just default use analog read, these 3 bits are all set. They're all set as 1, which means my division factor is 128. Now, that's going to get me a really, really good 10-bit stable ADC value. And it's going to take a long time to do it. And there's a bunch of code in analog read that you don't actually need, but it's nice to have. Okay? And it's taken time to run. Okay? So you're not running at full potential. You're not running it however fast you can run it. So instead, what we're going to do is we're going to set up these 3 bits that are inside this. These 3 bits are inside the register ADC-SRA. All right? So what I'm going to do is I'm going to set up some prescaler numbers. So prescaler 16, well, all I have to do is set up ADPS2 as a 1, right? 100. As 128, everything's a 1. Is this okay? I could have also used the _BV macro right here, but this is essentially what that macro does. Is that okay? You guys good? Someone with me? Yeah, look back at the slides. We're good. Okay. So, so now when I actually want to use this, I'm going to say ADC SRA and equals, not prescaler 128. What am I doing? I'm clearing the bits. Bam. I thought somebody would say datasheet. All right. Now I'm going to say ADC SRA or equals prescaler 64. Awesome. So now I can run my ADC at 250 kilohertz. No. So, well, I mean, you can and equal the only, you just want to make sure that the only things you mess with are those 3 bits down at the bottom. All right, because there's a bunch of bits up here, 3, 4, 5, 6, and 7. Those bits, they do stuff, and you don't want to mess with them. All right, if you don't know what it does, don't change it. All right, because you could change the entire functionality of the microcontroller by just setting 1 bit wrong. Right? It's like, oh, this is not for ADC anymore. I'm gonna actually recycle the clock and send it down here to the blow-up mechanism. Okay? You don't know. You have no idea unless you look at the datasheet. All right? So the problem with this is, okay, so here's my prescaler. It's 64. The problem with this is, oh, I go back and I look at the datasheet and it says, well, the full resolution of the ADC, that one ADC, it has to be running at less than 200 kilohertz for me to get full resolution. Okay, that's as fast as I can run that thing in there, right? So I have 6 different pins that feed into that, right? If only one of those pins is active, that means I can run one pin at 200 kilohertz. Not that 15 kilohertz that they were talking about before. I can run one pin as fast as I want. That's true. I'm not kidding. So that's fast, right? That's pretty good. So now we're fast, all right? So, are we that fast? I don't know. Are we that fast? You guys tell me. Are we that fast? Are we as fast as we need to be? Are we as fast as we can be? No, probably not. Why would I ask you that if it wasn't? Analog read wastes time. It's doing a bunch of Arduino stuff that we don't care about. All right? So how are we going to figure that out? How are we going to get past this analog read thing? We're going to write it ourselves. And how are we going to do that? Yes! Oh, I got you guys going. Let's do this. All right, so the fastest ADC possible that you can do not use the Arduino library. Instead, we're just going to read from registers. And we're going to look at the datasheet. We're going to figure out how to do that. I'm going to use this code right here, which we set up before. All that does is set up my prescaler as 64. I want to run at 250 kilohertz. All right, that's what we did before, these top 2 lines. Then, I want to run these 2 lines. I'm going to set pin mode A0 as an input. All right, it's an input now, right? So I set it up as an input, and then I'm going to enable the ADC by using this. I'm going to set my ADC SRA, and one of those bits in there is an ADC enable. So if I turned it off, I'm going to be SOL. All right? There's another little TLA for you. All right, so we're going to use these registers that we set up to directly read from the ADC value. The way that we do that is through this. So I created this little function right here called ADC_read, and it takes an input, a byte input, which is ADCX. That's the analog pin that I want to read from, 1 to 7. Okay? Bit masked. Right? It's a 1-hot ADCX. Does that make sense? Right? So if I want to read from pin 0, then the 0th bit better be 1, and everything else better be 0. Okay? Good. Rockin'. Okay, so there's this register here, which I've got, this is the data sheet for it, it's ADC mux, and that's my multiplex selection register, right? So I AND this with with F0, 1 1 1 1 0 0 0 0, right? Okay, good. We all know hex, right? Okay. All right, we're good. All right, so the first thing I do is I clear these bits down here. All right, I clear the bits, and then I set those bits. as ADCX1. Wow, I just told you a lie then. That is not 1 hot, is it? This is my mux selection bits, right? So look in the data sheet for how we want to send those in to actually select the pin. Okay, I think you actually just send in the number. Fair enough? Okay, so if it was 1, you'd get 1. So we're going to do the selection 1 through 8. Okay, so we set, also this line right here, this F right here, that actually sets up the reference from these top 3 bits. Okay? I wrote this code and I'm forgetting what it does. All right? So we set up the reference of these top 3 bits. We select the analog pin that we want with this line of code. And then we're going to do this down here. We're going to, if I look into this data sheet here, I've got this ADC enable. ADC start conversion is bit 6, right? And bit 6 is called ADSC, right? So I'm going to say, okay, ADC SRA or equals, bam. And I'm going to set that bit, which is ADSC, which is start the analog conversion. Then I'm going to sit here, and I'm going to say, while that bit is still set. Whenever that bit gets cleared, the conversion is done. Okay? So I'm going to sit there until it gets done, and then I'm going to return this ADC, which is another register, which is the ADC value that it came back with. Okay? And I'm going to return that value as an integer. Start conversion, wait to be done, and then return. And now we're fast, right? I'm going to eat that rabbit. Or maybe we're just going to catch him and, I don't know, invite him to tea. Whatever you guys. I didn't expect the It's fine, whatever. That is an awesome shirt. All right, ADC summary. I like anything with math on it, really. Okay, so when you're setting up your ADC, try the analog read first with no adjustments, because it's going to make your life a whole lot easier. Okay? If it's not fast enough, go in, try that prescaler code that we talked about before, but still use analog read. If it's still not fast enough, you're pulling your hair out, you're like, oh my gosh, I need to squeeze some more microseconds out of this microcontroller, then go in and use that ADC read. Okay? For the assignment that I give you, you can use analog read all you want. Okay? Not even set up prescalers. But for the final assignment, if you're working with something you really need that precision, here it is. Good?
So it's not fast enough, it starts losing stuff, or it just...
Oh, yeah. So if it's not fast enough, if you need a higher sampling rate. Yeah. If you need a higher sampling rate, this is how you do it. Right? Now remember, because you have control over this, like if you sample too fast, you can go ahead and sample at 16 megahertz off of this pin. All right? That would be ridiculous, but you could do it. If you did it, your ADC would have a resolution. It would be a digital pin. It's 0 or 1. All right? It has like 1 bit of precision, maybe. All right? Don't sample at 16 megahertz. I wouldn't go much lower. In the data sheet, they tell you, don't try not to go below 64. Okay? Don't increase the clock frequency above 250K. Okay? Because you start losing a lot of bits. At 250K, you got about 8-bit resolution. But there's a whole equation if you want to go figure it out. Right? Which I'm guessing you don't. Somebody does. You don't know. Okay. Potentiometers. Coolest thing in hobbyist electronics. No? They're pretty chill. All right. So the potentiometer, essentially what it's going to do, the whole end result of it is, all it is provides you a way, you've got 2 resistors, right? And voltage, you can measure voltage over resistors, right? A potentiometer adjusts the resistance in there so that if I have, 5 volts on one side and ground on the other, the pin in the middle is adjusting because I'm changing the resistances between 0 and 5 volts, depending on how I adjust the little mechanical switch that's inside there. Okay? So, how many people have used a stereo? What do you think the volume knob is? Is that the This Is Spinal Tap reference? Yeah! Did I already say that in class one time? No? No? Fine. It's cool. I like it.
Is it not a rotary encoder?
It could be a rotary encoder. Wow, look at you. All right, yeah, it could be a rotary encoder that's actually doing some things in there. Which, like, if you spin the dial and you can just keep turning it, it's rotary. Yeah, it's a digital dial. Okay. Right. But most of them, anything built before 1996 is a potentiometer. All right. Sweet. So it's got 3 different pins on it: V+, ground, and an analog out. And the analog out is almost always in the middle. Okay? So let's do an analog read demo. Let's do this. Got this covered. Whoops. Oh, you know what? I need to talk about the Lookin' Live demo. I will do that right after the analog read demo. All right, here we go. Rocking this out. Analog read serial. I did not write this code. This code is in the public domain. I got it from Arduino when I downloaded Arduino. I went up here, I said File, Examples, Basics, Analog read serial. It is the first example for using Arduino. This is pretty cool. All right, so what does it do? Okay, I'm going to say serial.begin, right? I set up my serial port, 9600 baud. We talked about that last time. I'm going to loop over this. I'm going to get that value of A0, and I'm going to print it to the serial port. I'm just going to read from it and then send it to the computer on that serial line, right? The USB, right? The USB is an emulated COM port, all right? And then I'm going to delay 1 millisecond, right? And then I'm going to do it again. So I'm just going to read really, really fast in between, okay? And spit it out on the screen. Let's do that, okay? So let me get you some video. All right, so here is my microcontroller setup that I have right here. Pin A0 is connected to this little, oh, come on. Wow, this is unbelievably difficult to do upside down. There, I'm wiggling the wire. That is connected to A0. That's an analog pin, okay? On the Arduino, I've got some other things, which are things like 5 volts and ground that I can connect that to. Or I connect it to 3.3 volts, okay? Right? So, let's see what happens when I take that pin and connect it up to something, right? I'd hoped to have a potentiometer here. I left it in my office, okay? Fine. All right, so analog read. I'm going to upload this to the, I don't know if I've actually set this up correctly. Hey, it's uploading. Okay, so let's go to the serial monitor. We're running at 9600 baud. Let me do this. Let's take this over. Whoop. Really? Ah, fine. Okay, so I'm going to touch this pin. What's it reading? It's floating. That is the voltage on my body. Okay? Everybody has voltage surging through their body right now. Do you know why? Why? No, this is man-made. Because we use power. All of these little electrical signals in a line right here, every single person in here is radiating 60 hertz. Okay? You have been since you were born. Since before you were born, you've been radiating 60 hertz. Unless you were born in the middle of the forest. Okay? You could have been. I don't know. Oh, no. Electrical power lines. Power lines. Power lines radiate 60 hertz, and your body is an antenna. You pick up 60 hertz, and it runs as voltage across your body. I know. We wrote a paper about it. It was awesome. Okay? You can use that to control and figure out people's body movements because they radiate 60 hertz, and they're an antenna. Right? Now you're a different antenna. Now you're a different antenna. And now you can figure out people's body positions. Okay? All right, now, back to my demo, though, because I was going to... Okay, so I'm going to connect this up to ground. Bam, I'm connected to ground. And look, they're all zeros. So happy with myself. I'm going to connect this up to 5 volts. What's going to happen? Yeah. What happens when I connect it up to 3.3 volts? I should get a value in the middle. What should that value be? 700. Yes, that's not a bad. Let's see. 3.3 volts. 665. Yeah. Is it 665? Is it? Oh.
It's having trouble.
All right. All right. So that was my analog read demo. Good? Happiness? Excellent. Moving on. Everybody knows, so I can set up that reference to be different, right? I don't have to set it up to be 5 volts. I can set it up as 3.3 volts. And then when I put that 3.3 volt pin on there, that's 1024. Or if I put 5 volts on there, that's also 1024 because it's just above 3.3. Anything in the middle between 0 and 3.3, divide by 1024. And we're happiness and we're moving on. Okay. Now, looking live. Let me just really quickly go over this because I sent out an email, very cryptic, with a lot of typos in it. That was essentially, it was like, hey, why aren't things working when I change my phone orientation? Well, here's why. Xcode, preferences, class projector, boom. Okay, so going back to our iOS development stuff, we created this thing called Looking Live where it took my face and it found it and it distorted it and it made me have a little itty bitty nose, okay? And that was the whole point of this entire project that we had. So it works great when I'm in landscape left mode, right? And when I turn it, it's like, what did you just do, right? Okay, so do you guys know what I'm talking about here? I think at least half the groups know what I'm talking about here, okay? Because I've had questions about it. Okay, so the problem is that I set up this options parameter right here. I say options, you know, CI detector image orientation, blah, 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 blah. And I get the image orientation so that I can send it in to my facial recognition algorithm and tell it what orientation the phone it is so it knows where to run. So I did. I set it up. It's right here. Here's my options. Where do I use options? Nowhere. Nowhere after I've set it right here, right? Like I use options up here as well, right? And I use it in the detector. But then I set options here and never use that set of options again. All right, what should I do? Detector features in image options. And then the options that I'm going to give it is ops. Yay! So now, what happened? Oh, it's running. It's too dark. Come on. Okay, so I turned it this way. Landscape left. Oh, it doesn't get it. What if I turn it upside down? Oh, I didn't turn it on. So it gets it. What if I turn it this way? It doesn't get it. Oh no. What if I turned my head upside down? I can't do it. Okay. Anyway, let's just go fix the problem because I know what the problem is. Okay. So the problem is that I need to go in here to video analgesic. I need to find that function, which was CI orientation from device orientation. And then I need to change over here. It says, okay, UI interface, landscape left. I'm going to give it a 3. Actually, I'm going to give it a 1. Landscape right, I'm going to give it a 3. So I'm going to switch those things around. Now I'm going to run it. Hey. Good. Good. Oh, man. Why do I always do that? Okay, here. Oh, man. Okay.
You're saying it would have worked if your head was upside down.
It would have worked if my head was upside down.
All right, excellent.
Excellent. Oh, it got me. Oh, moving around. Oh, come on. I'm moving around. Oh, it's tracking my face pretty well. Not so bad. This is good. This is a good look for me. All right. I even got it in the low light conditions. Okay. So I'm going to turn that off because it's going to keep freaking out. Okay, so we're good on Looking Live demo. We're good on analog read. All right, moving on. Webcam me. Stop it. There. All right. GPIO, General Purpose Input Output. Okay, we've learned about ADCs, we've learned about pulse width modulation, we're feeling super happy with ourselves. Now we're going to learn about digital input and output. Okay, so digital I/O that's on a microcontroller, it is buffered, which means that I can set it as digital high and digital low, and it can drive current off of the pin. Okay, current is power-ish. Okay. Essentially, for each of the pins that I have on my microcontroller, each of the 13 digital I/O pins, the GPIO, I can source out about 40 milliamps from those pins. Okay, that is enough current to brightly lit an LED. An LED usually runs at about 20 milliamps. Okay, so essentially, if I run 40 milliamps through that LED, I can make it really bright. Okay. There's a max, yeah. You can source 40 from each pin. You can't source 40 from all of the pins at the same time. I think at maximum, you can probably source out 200 milliamps combined to all the pins. Yeah, so if you were going to drive like an LED array of stuff, you would have to, you could only drive like, I don't know, 5 of them at a time, right? So, right, you can, but you could pulse them at different things like this, and you could do it. Okay, it's multiplex for different functions, right? For instance, pins 0 and 1 are actually the pins that are going up and down that are communicating back with the USB, which is my serial port, right? It's all of that ASCII text that I'm displaying, like when I did my analog to digital conversion. That was all converted on pin 0 and 1. So all of those GPIO pins have some functionality, and you got to look somewhere. Data sheet, yes. All right, to figure out what all of those functions do. There's these things called pull-up resistors that are on each of the pins. And essentially, you can enable or disable those resistors. Arduino auto-enables the pull-ups when you're using them as inputs. It disables them for outputs. This slide needs to be updated. That is not true anymore with the current Arduino sketch. I will show you that here in just a second. You don't know what pull-up is? Well, let me give you a slide. All right, so atmega GPIO. So when you set up a pin, right, you can set up pins 0 to 13, right? So there's 14 pins that you can set it up on. If I want to set pin 2 to be an input with a pull-up, then I give it this command. If I want to set up pin 3 to be just a digital input, which detects that pin is either 0 or 1, I just set it up as an input, or it could be an output, which is 0 or 1. Right? 0 or 5 volts, logic levels. Okay? So here's my microcontroller over here, and here's the output. All right? This is where I'm connecting it to the world, is my output. In between that, right up here, there's this thing called a pull-up resistor, which I can enable it. And if I do enable it, it connects that resistor to the power source for the microcontroller. Well, what does that do? Yeah, remember that analog pin that I set up? I grabbed it. Like if I didn't grab, and I'm in my analog read demo that I just did, it was reading the voltage on that pin, and it was just going crazy all over the place, right? The pull-up resistor was not enabled. The voltage was just going everywhere, okay? So here's what I want you to think about this as. I want you to think of each of those pins. It's a mechanical lever arm, okay? Right? And when that arm is down, it's logic 0. When the arm is up, it's logic 1. And the pin is detecting whether or not the arm is up or down, okay? Well, when I connect it to something that is driving that pin low, I get 0 on my digital pin. When I connect it to something that is driving that arm high, I get a logic high level on that pin. If I don't have anything that is driving that arm, boom, my driver disappears. What is my lever doing? This. It's a lever in the wind. All right, Elton John would be proud. Okay? You guys are tough, man. All right, what do I need to do? So I enable that pull-up resistor. That pull-up resistor is like a spring. Bam! It's attached to the lever right there that says if nothing is driving that, I've got a very weak spring that's going to pull that lever up so that it's at positive 5 volts when I got nothing connected to it. That's my pull-up resistor. It's my spring. Good? Happiness? All right. So if I want to read from the pin, see whether or not that arm is low or high, I just do digital read, pin 2, and I get an int back. I get a int back. All right? Even though this could be represented by 1 bit of information, it is true or not true. When I do digital read, I get an int back, okay? Which is 0 or 1 as an int, okay?
Is it always 1, or can it be any other value? Other than 0?
No, it's digital. It can only be 0 or 1. It is logic high, logic low. Okay? So that's a GPIO, right? So the digital pins are separate from the analog to digital pins. The analog pins are the ones that can actually give you a value, right? Digital pins are 0 or 1, right? I could actually, if I have 8 of them, I could just read a byte and get all of those digital pins, right? Because it's just 1 or a 0 depending on which pin on it.
And why did they give you an int?
Why do they give you an int? It's Arduino.
It's the smallest. Isn't int and C the smallest?
I think it's the smallest thing before, like you have to type def a boolean and that type of stuff. So I think it is. What's the problem with this? It's terrible. It's inefficient. It's slow. It's probably suitable for everything you're going to do. Just in case, we're going to talk about fast access. All right, so here's my atmega GPIO, right? I've got this thing called DDXin and port XIN, which I am going to set. These are the registers for which I can set up all of the different pins on my microcontroller. I can set them up as inputs, I can set them up as outputs, I can set them up as inputs with pull-up resistors. And these are the ports that I'm interested in, those 2 values. So, if I set port B right here to be that string of values, hold on. If I want to read from the register, I want to read from pin B, I can say byte pin values equals pin B. Okay? That returns all of the digital I/O values that are on pin B. Pin B is an 8-bit register. Okay? So if I want to know, pin B has ports 0 through 7 on it, right? So the first bit represents the digital high or low on pin 0. The very last bit represents digital high-low on pin 7. Okay? So if I want to read those out, I got to go through that byte value and just basically bit bang it. Okay? Good. Okay. Now, what does this do? We've looked at data sheets now for long enough. You guys tell me, what does that do? Okay, first of all, what does the first line do? What does port B? Yep, it's setting value. Okay, so it's setting B7, B6, B1, and B0 to be logic 1. Okay, and then there's this thing down here called DDRB, which is setting the 3, 2, 1, and 0 bits. Okay, so if I were to read those registers out, I would get this. Port B looks like that. Okay, so as I'm setting up these things, you'll notice that if I want to figure out what this is set up, I go from here and I look at this logic table to see what it does. Right? So these right here, this is 1, 1. Okay, for the 0th bit. Right? So 1, 1 means that I am setting that up as an output with no pull-up, and we're good to go. Okay, output, no pull-up, and it's output high. Right, if it's 1, 1. Is everybody okay with that? So this is high. This is digital output low. This, I've set it up as an input, no pull-up resistor. This, I've set it up as an input with a pull-up resistor. Okay? And now I can read from it using byte pin values equals pin B. And I can read from it as fast as I can. It's just as simple as one clock cycle reading from a register. Right? Good. It's my one, I can run this at 16 megahertz. We're good. Okay? I cannot run digital read at 16 megahertz. You guys okay with that?
Wait, so
Whoop,
each
whoop.
of those little 2 bits corresponds to a pin?
Yeah. Yeah. So this is pin 0, 1, 2, 3, 4, 5, 6, and 7.
Why does 0, 0 have a pull-up? It says no on pull-up.
0, 0. Pull up. No. Yeah, you're right. Switch them.
Yeah.
Switch that. Oh, wait. Everybody switch that if you're watching the video. Okay. So we're good. All right. So, connecting to mechanical devices like a switch. How are we on time? I have no idea. I've got like 20 minutes. 20 minutes. Okay, so I've got 25 minutes. So, no, okay. All right. So, one of the things that you can do with this is you can create a button, okay? A button is just a mechanical device. If I press it in, it makes a connection. If it's not pressed in, it doesn't make a connection, okay? That's what we call a normally open switch, okay? Normally it's open, then when you press it, it closes, okay? There's this nice little pull-up resistor that's up here. Maybe I've got my own pull-up resistor that I'm using. Maybe I'm using the pull-up resistor that's internal to the chip. But essentially, what happens when this mechanical pin right here is not connected to anything, when it's normally open? It's pulled up to VCC. That's my spring pulling up my lever. The second that I punch that button down, I pull it down to this value, ground. Goes logic low. Okay? So everything is it. That's as easy as it is if you want to set up a button on a microcontroller. Okay? It is that easy. It is not that easy. Why is it not that easy? Yeah. Yeah. Whenever you press that button, you essentially, it's mechanical, right? So it does this. When it tries to close, it bounces off of it. And so you're running at 16 megahertz. You see every connect, no connect, no connect, no connect. Okay, connected. And that thing. So now you're running like this. Why is that a bad thing? Yeah. What if you all you needed to know was, hey, how many times does that button get pressed? Right? All of a sudden you're running at 16 megahertz, one press, you're counting it as maybe 64 different presses. All right? Not good. How do you do that? How do you fix this? Yes, you can do that. You can also solve this in hardware with something called a Schmidt trigger, but usually you're not going to use that unless it's built into the microcontroller. This one does not have a built-in Schmidt trigger. If you don't know what a Schmidt trigger is, don't worry about it, because we're going to do it in software. Okay, so connecting to mechanical devices like a switch. Essentially, what you're going to do is have this little thing called a debounce. All right? And you're going to say, okay, if I'm reading from the switch and it doesn't equal the last button state, I'm going to say, okay, my last debounce time is the current time in millis. That's what this function does. I'm going to say, what's the current time when this button was pressed and it didn't match what the button before it was pressed? Okay? Anytime it changes from high to low or low to high, start that time. This is my last debounce time. If the current time minus my last debounce time is greater than some debounce delay, then, bam, I'm going to do some logic. I know the button has been pressed and it's only been pressed once. Okay? This is so that you can do one press versus like a double tap. Okay? Does this make sense for debouncing? Okay. The biggest use of debouncing is going to come when you're using a GPIO as an interrupt pin. Okay? There are two different interrupt pins on the atmega 328, which is the Arduino Uno. Okay? Oh, man. interrupts are either from external or internal triggers. Okay, so all this means is that you have dedicated hardware that is looking for something to happen on one of these pins, or looking for something to happen in one of the registers inside of the microcontroller. Okay? So whenever that trigger occurs, right? So maybe this is like you want to be triggered when a pin goes from low to high, right? The rising edge. You want to get a notification. What happens when you essentially get that notification, the main loop stops executing right where it is when it gets that trigger. Okay? It stops running. All of the local variables and the instructions that it's running right now, those are all copied over to the stack. Okay? And then it goes over. Oh, yeah. It also turns off all of the other interrupts that are on your microcontroller. Okay? So I just got an interrupt. I'm turning everything off so I can deal with this interrupt. Then I will turn those interrupts back on. Okay? It calls an interrupt service routine. What's that interrupt service routine? Whatever you want it to be. You define the interrupt service routine, right? This is your pin. You told me you wanted to know when it got high. I don't know what you want to do with it. You do something with it. No? Okay, fine. After execution, the stack, everything that it put onto the stack, it reloads back into here. All of that stuff from that it put on the stack in the local memory, and the main loop just continues from where it was. Question?
If you're going to overwrite interrupt service routines, though, that already have functionality on the microcontroller, like it's looking for a reset pin being pressed or something like that, then you have to, if you're going to multiplex it, you have to be sure to call the other service routine if it wasn't your interrupt.
What does that sound similar to? Yeah, kind of like method overloading, kind of like an inheritance. It's actually a flatter. It's protocol, right? That's a protocol. Yeah. So essentially, if you are getting an interrupt service routine on a pin or something, an internal register, it's like, hey, whenever that goes high, call this interrupt service routine. If there was already an interrupt service routine that happens for that the microcontroller is running, you have to call that function. You have to make sure that what was supposed to happen happens, right? Or else you are messing with the function of the microcontroller, the raw core functionality. Okay? Happiness? We're not going to mess with most of that. Okay? All right. So, if I want an interrupt, this is the code to do it in Arduino. Attach interrupt. I'm going to attach it to interrupt 0. I want you to call this interrupt service routine SW_ISR. Notice here that that is something that I have named, SW_ISR, software interrupt service routine. Okay? That's a name of it's a name of an interrupt service routine. It's in all caps, and I use underscores, and that's convention when you make an interrupt service routine to make it all in all caps. Okay? You don't have to. You should. Why should you? Because I told you to. Why did I tell you to? Someone else told me. Okay? Now we're moving on.
Wait, what's the 0?
All right. The 0 means to select pin 2. What? What's going on there? The data sheet. Look at the data sheet. The Arduino Uno is built on the atmega 328P. The atmega 328P is your microcontroller, and it has 2 external interrupts. One is on pin 2, the other's on pin 3. Okay? Arduino works with more than one microcontroller. So it's saying, okay, attach the 0th interrupt to the very first interrupt pin that you can do it to. That's pin 2. You can also do it on pin 3. Okay? If you need more than 2, then you need to go get a, what is it? It's an ARM. Yeah, essentially. You can also get another Arduino. There's an Arduino Mega or Demanuelev. I don't know how to pronounce it. Does anybody know how to pronounce it?
The Mega. They have the Do, which is
The Do. That's what it is. That's what I'm thinking of. The Do. The Do has like 16 interrupts and 64 GPIO. All right? So that's pretty cool. You can work with that. All right. So Uno, pin 2 equals 0, pin 3 equals 1 for attaching an interrupt. I'm going to say, call this routine. It's not a function. Why is it not a function? No parentheses after it. I like your style, but what else? It doesn't take input. All right? It is an interrupt service routine. I can't take, okay, and with this variable. All right? It's not a notification. It is a service routine. Okay? It's just the distinction, know the vocab. All right. I could also say that I want it on the rising edge, the falling edge, whenever it changes, or call this interrupt routine whenever that pin is low. Okay? What? You can do that.
No high?
There's no high. You can do it on the do. The Dewey, I don't know. How do you pronounce it? We'll call it Dewey. All right? Dewey. It's going to go this is Dallas style. We're calling it Dewey. All right? Good. Okay, so here is my little interrupt routine. So here's that. Blink LED equals not blink LED. What does that do? Toggles the state of the LED. Bam. Okay. Oh, this blink LED. Boolean. It's a Boolean. It's volatile. What? Why would I do that? So that it can be changed by the service routine. Yeah, so essentially, any variables that you're thinking about changing that are going to be inside of an interrupt service routine, standard practice would be to declare them as volatile. And the reason that you want to do that, you only do this when you're writing in C code. But essentially, the compiler will look at some code. And if you say, okay, I have a variable that equals 0, and I'm going to say, while that variable equals 0, do this stuff in here. Okay? The compiler will see that, and it will say, well, that's not, I don't need to do all this. That's while true. And it will optimize that away. The problem is you have an interrupt service routine, and you can change the state of that variable inside of your interrupt service routine. If the compiler has optimized that out, guess what? You're not controlling anything. Okay? Declare it as volatile so that the compiler knows not to do those types of optimizations. Fair enough? Fair enough. You can switch on and off interrupts. Let's say you get to a parse in the code, and you say, I do not want any interrupts to happen in this code. It's time sensitive. I need it to happen. I'm going to call this function no interrupts. And then I'm going to do my code, and then I'm going to call this function interrupts to turn them all back on. Okay? Awesome. Well, Arduino doesn't really give you full access to using all of the interrupts that are in your microcontroller. So if you wanted to do things like timer interrupts, like you want to look at a timer that's actually sitting there running, I want to get the interrupt. I want to overwrite the interrupt service routine for when that timer goes off or when it overflows. Well, you can do that, but we got to use the AVRC code. All right, here's my counter. I've got a counter that's doing this. Bam. It's a timer value, just like we used in the pulse width modulation. All right, so I want to generate an interrupt. I go like this. I'm going to have my counter. It's going to go up to a max value and start counting back down. Max value, start counting back down. Whenever it gets to 0, I want it to call my interrupt service routine. Okay, how do I do that? Oh, how do I do that? With the data sheet. And this code. Okay, so isn't it so much better to just say attach interrupt, right? So much better, but you can't do it. Doesn't give you full control here. So essentially, we're going to have a bunch of different registers. The first one that we're going to set here is I'm going to clear control register A so that I can set up my own timer. And then I'm going to say, okay, here's register TCR1B. That sets my pulse width modulation to phase correct mode. What does that mean? It means that I'm counting up, counting down, counting up, counting down, instead of counting up, down. Counting up all the way to 0. Counting up all the way to 0. Okay? So count up and then down. After that, well, I want to figure out when I'm going to call this interrupt service routine because it's going to be periodically called, right? Let's say I want it to be called using the variable microseconds. Okay? Well, then I need to figure out how many cycles I need to run on this counter that's running at 16 megahertz, right? Before I can get to that number of microseconds. Essentially, what I want to know is the period of this right here. Okay, so I can set that up properly. All right. So the way that I do that is I use f_CPU. What's that? Yeah, frequency of my CPU. It's 16 megahertz. I'm going to say 16 megahertz divided by 2 million. What does that do? If I were to divide it by 1 million, what would that do? Yeah. It would convert it. It would essentially convert it over to. It essentially converts it over to the length of time that happens for one clock cycle. Okay. Why am I dividing by 2? Because it goes up and all the way down. Okay. So if I take that and I multiply by the number of microseconds, that's the number of microseconds. That's the closest cycle that will get me to the number of microseconds when this thing counts all the way up and all the way down. So I convert microseconds to cycles. And then what I'm going to do is set this register right here. That's the max value of my counter. That's how high it's going to count up to. And then back down. Right? So maybe that makes a little more sense of what I was doing up here with cycles. Then I'm going to set the prescaler, which is going to divide down my clock. And essentially that prescaler, that gets set right here. Okay? And you can go through that code if you want to. I think it's going to take a little too much time and I want to keep going. Okay? I don't even know if anybody will use this. Okay? But if you do, and you need it, it's here. You might use it. There might be one team that uses it. Therefore, this slide exists. Okay, then I'm going to enable an interrupt from the pulse width modulation using this code right here. So there's some register. I'm going to set a bit that says, hey, I want to use an interrupt service routine here. All right. Did I provide you with the... I'll post an example of this so you can see exactly what it does. Okay? Essentially, there's some Arduino code so that you can grab this bit and get the interrupt service routine off of. Wow, I'm fading now. Okay, here we go. Servos. There are 2 types of servos. How am I doing on time? 5 minutes. Could do this. There's 2 types of servos. One is a position servo. It means, okay, I want you to rotate to a position. Okay, a servo is a motor, by the way. All right? And I'm going to say, okay, if it's a position servo, I want you to go to a certain position on the wheel. Right? I want the wheel to go to 15 degrees and stay there. There's also something called a continuous servo. That can spin all the way around, one way or the other. And when you send control signals to that kind of servo, you're going to say, I want you to move 3 degrees clockwise or 3 degrees counterclockwise. Okay? The way that you control all of that with either of these types of servos is through pulses. What does that mean? PWM. Yeah. So, if you have a rotational servo, you're going to have this repeating pulse train, and the pulse lengths are going to be anywhere from 1 to 2 milliseconds long. Okay? So essentially, if I want this servo to be at this position right here, right, then I'm going to send it a 1 millisecond pulse. Hold this position when the pulse is 1 millisecond long. All right? Move to and hold to this position if you are getting pulses that are this wide, 1.5 milliseconds long. All right? And essentially, you can give it all the way up to 2 milliseconds, and you can turn that thing from 0 to 180 degrees and back and forth and back. Okay? As you control the pulses to it. So this servo can move from 0 to 180 degrees. Some of them can go from 0 to 360 degrees. Depends on the servo you get. Most 0 to 180. Okay? And it just depends on those pulses that you send to it. Arduino servo makes it really, really easy to use a servo. All right? So, you don't want to see me. Yeah. Okay, so you include servo.h, and then you say servo, my servo. you can have up to 6 instances of this class on the Uno, right? Because there's 6 different pulse width modulation outputs. So you can connect up to 6 servos. Okay? Then you call this thing right here my servo attach. Right? This is going to use pin 9. I'm going to say, okay, do pulse width modulation on pin 9 for this servo. And then I am going to do an analog read on one of the A0 values. And depending on what that value is, that's going to give me a value back between 0 and 1024. I want to map that to 0 to 180 degrees. Right? So I call this function map that value. It goes from 0 to 1023, but I want you to map it down to a value between 0 and 179. Right? Linearly, map it down. Give me a value back. Then I'm going to do myservo.write that value, and then for the end of time, I could do whatever the hell else I want to do on this microcontroller. That is going to hold that microcontroller at whatever that potentiometer pin value was. Okay? Makes it really, really easy to do. So if I want it to be at 80 degrees, I just send it 80, set it and forget it. Okay? And then I do whatever I want with the microcontroller. If I want it to be 90 degrees, I set that value as 90. Good? Happiness? Easy to use? Right? Why would you use a servo? What do you use a servo for?
Robot hands.
Robot hands. Yes, robots are made with servo motors, right? Because if I'm making an RC car, right? I got one motor spinning the back wheels fast as I can, right? Because we love fast, right? Just love it. Cheetah speed, right? That's not a servo. Guess what is a servo? The direction. I'm going to move my axles. Left, right. And I can control it. All right? Good? Happiness? Continuous servos. Am I good on time? Yes. Somebody said sure. Each pulse is a new command. All right? The pulse width is going to be the angle that you move from the current angle. So I'm going to have a servo that can rotate all the way around counterclockwise or clockwise. So if I give it, for every single pulse that I give it, I'm going to tell it to move a certain number of degrees. If I give it a 1 millisecond pulse, that means move 165 degrees clockwise. I only gave it 1 pulse to tell it to do that. And then I'm not giving it any pulses. I'm going to wait till it moves all the way 165 degrees. Okay? If I give it this pulse, right, as I get closer to 1.5 milliseconds, 1.5 milliseconds is neutral, right? So this one's going to move clockwise 80 degrees. If I give it a 1.5 millisecond pulse, that says don't move. Anything greater than 1.5 milliseconds, move counterclockwise 80 degrees, move counterclockwise 165 degrees. I'm guessing that means class is over. All right. We will do a continuous servos demo right off the bat next time, and then we will go straight into Bluetooth, controlling the Arduino from your phone, and vice versa. Are you guys as tired as I am?